Alright, so now we have some things to look out for calculations instead of just random items. We can calculate density in air. This presentation should also be a little bit shorter. We are looking at 5 slides of information. Starting off with density. Density is an important characteristic of matter. It is an intensive property, meaning that all pure substances have a specific density, so it's characteristic of that item's identity. So when one speaks of lead as being heavy or aluminum as being light, we're actually kind of thinking about density with those metals. So we have masses of them or matter of them that maybe they look like they're the same size, but when you hold them, they feel completely different, like they're taking up the same volume but feel different. So density is actually defined as mass per unit volume. So we can look at the formula. D is density, and then we have M for mass divided by V for volume. So these are some things that we'll be looking at, and keep in mind we did talk about units for these measurements in our first PowerPoint. So mass would be using grams, and volume would be using milliliters or centimeters cubed. Also, you can see this is a calculation, so that is a prime example of a derived measurement or unit. When calculating density, the formulas once again are up there. It's in their verbiage as well as symbols. So an example would be we have an object with a mass of 10 grams and it has a volume of 5 centimeters cubed. So it sounds to me like this could be a little box of some sort. When we calculate it, we use 10 grams divided by 5 centimeters cubed. So in your calculator, you only have to enter the 10 divided by 5, and that gives us the answer of 2. Notice I only have one sig fig there. There is no decimal in the 10 grams. Our unit then is grams divided by centimeters cubed, or grams per centimeter cubed. So you really need to read your question, because volume can be given to you directly, or you may have to calculate it. Remember we said it could be giving you the length dimensions for length times width times height, and then you'll have to multiply those to get centimeters cubed. Or you could use displacement, meaning a grad cylinder was used and you have a volume of water, and then you add the object and you have a new volume of water and you have to subtract the two numbers. So that is something to watch for. These problems do not have to come straight forward. We could also not be solving for density, but solve for mass or volume. So let's look at a way to help us out with that. I call it the density pie. Most pies that you do make are pretty dense, so I guess that makes sense. Our formula, if you look at the circle, we have D for density, and then we have mass written above the line and volume written beside the line. If we are solving for density, we can put our finger over the D, and you get M divided by V. If we want to solve for mass, we can put our finger over the M, and that would tell us we have D beside V, and that means we have to multiply. So density times volume will give you mass. If we want to solve for volume, we can put our finger over the V, and that gives us M over D, so it'll be mass divided by density. So the density pie can help you rearrange the algebraic equation without actually have to rearranging it. So it's a nice little graphic organizer that would be useful in your note cards. Our base units for density is kilograms per meter cubed. In a lab, we will use grams per centimeters cubed or grams per mil. Once again, that was mentioned in our units note packet, so we can look at it different ways. The next topic we have is determining error. So we want to know, how wrong are we? In order to do this, we have to have two components. We have to have an accepted value, meaning a starting point, a correct value, or a reliable value from research, or the accepted value. We also need to have an experimental value. this value comes from an experiment that we did, so we're comparing standards versus a lab-generated number. We could also be doing before and after numbers. So the before would be the accepted, and after we manipulated the matter, we have the after, or the experimental value. Error itself is looking at the accepted value minus the experimental. So just how different are they? And then percent error, we divide it by the accepted value. So we're looking at how much did we have wrong divided by how much we should have had. So let's look at an example for percent error. We have a measured density from a lab, and the experimental value is 1.40 grams per mil. The correct density is 1.36 grams per mil. Either that was given to you within the laboratory, or you looked it up and researched that item to see what the accepted density was. We need to find the percent error. So we look at our value, 1.36, the accepted. We subtract 1.40, which was our lab experimental value. It really doesn't matter which one comes first. That absolute value sign is our saver. So the number will be the same. It's just whether you get negative or positive in your calculator, just ignore the negative. It's okay. So we get that error, we subtract the two, and in this case, it will be 0.04. And then we're going to divide by 1.36. That is density. I didn't type the units in. I was having issues with getting all that in there, the fractions within fractions. But because we're using the same unit the whole time, it will cancel out and become 1. And just like any test score, we multiply by 100. So our answer would have been 0.0294, but when we multiply by 100, we get 2.94%. So here we have an example of a given density. Please observe the units, grams per mil, an experimental density, and we're looking to see what percent error is wrong. Coincidentally, if you have 2.9% error wrong, you can actually subtract that from 100. And if you do so, you get 100 minus 2.94. So we can actually say you have 97.06 of it correct. I don't know why we need to be negative in science sometimes, but sometimes we want to know how off an answer is instead of how right an answer is. So that is one way you can look at it.